Today we will study the chapter 5, which is the elastic materials, and we will study about the waves, and today we will focus on sound waves. Also, at the end of the presentation, I will explain how you will complete the pendulum mass and angle lab. Also, this week you had to complete the homework number 5, and here is the homework number 6 if you want to start working on it. Then in this chapter, we will focus on vibrations. Then the elastic materials, which are materials that recover each on its original shape after we apply some force and we deforms it, then that materials we can apply some force, we can deform and they can recover the original shape, they can vibrate. Then these vibrations can be, for example, can be the oscillation of the spring. This can be a vibrations, can be the oscillation of the pendulum, can be also the motion of the water in a U-tube. Yes. Can be also the vibration of the string in a guitar. All these are vibrations. These vibrations, we can see or we can hear that vibration. Yes, for example, when we touch the string in a guitar, we can hear the sound. Yes, we can hear the sound. However, there are some vibrations we cannot see because they are invisible to our sense. That vibrations involve heat, electricity, and light. But today we will focus first in the vibrations we can see or we can hear. Then what is a vibration? Then the vibration is a repeating motion that moves back and forth. This is a vibration. As for example, the vibration of the pendulum. This is a repeating motion that is back and forth. As this is the vibration. One thing is always the vibration occur around the equilibrium position. In this case, this line corresponds to the equilibrium position. It's around this line is where the pendulum is moving back and forth. Also, this is the spring and mass system. This also is the motion of this system is a vibrational motion because it's moving is back and forth motion and it's moving around the equilibrium position. As this is moving back and forth around the equilibrium position. Then this is also a vibration. In order to describe vibrations, we need to know several variables. In the same way when we describe the motion of the car, we need to know velocity, we need to know time, we need to know acceleration. When we describe a vibrational motion, we need to know some variables. Some of these variables are, for example, the amplitude. What is the amplitude? Is the maximum displacement around the equilibrium position. And if this is the equilibrium position, this point here is the maximum displacement. Yes, is the maximum displacement from the equilibrium position. This is also the maximum displacement, but in the opposite direction. And this maximum displacement is called the amplitude, and we can identify using the letter A. In this case, this is the equilibrium position, and this is the maximum displacement. In other words, this is the amplitude of the vibrational motion. This, and this is the amplitude in the other direction, in the opposite direction. Then the amplitude is the maximum displacement from the equilibrium position. A cycle is a complete vibration, it's back and forth motion. Then the cycle is a complete vibration or a complete oscillation. Then the cycle is moving from one point to another point and back again. Is back again to the original point. Yes, it's moving here and then back, one cycle. Yes, it's start here, one cycle. Yes, moving from this point back to this point, one cycle. This is important because you need to know this one when you conduct the lab. Another variable we need to know if we want to describe a vibrational motion is the period. The period is the time for one complete vibration. Then is the time to moving from here to here. Yes, this is the time for one complete vibration, for one complete cycle. Then how, because it's hard, it's difficult to measure just the time for one cycle, then usually what we can do is we can measure the time for 5 cycles, and if we want to know the period, then we divide this one by the total time, divide by 5. Yes, divide by 5 is where 5 is the number of cycles. Then if the n is the number of cycles, yes, and t is the time for complete 5 cycles, just we can think n equals to 5. Then what I would like, then the period is the ratio or is the division of the time for the 5 cycles divided by 5. Then let's try, can you take your cell phone and can you try to measure the time for 5 cycles? Then you can start here, 1, 2, 3, 4, 5, stop the stopwatch. Yes, now we stop. Then I did this exercise. Yes, I took my cell phone and I measured the time for 5 cycles, and to get a better result I did 3 times. Yes, this is the first trial, second trial, 3, and I got for 5 cycles the first time 11.70 seconds, 11.83 seconds, and in the third trial I got 11.69 seconds. And why I took 3 different times is just to get a better result, more accurate result. Then to get the time, this time we had to take the average of these 3 different times. And the average is, we add these numbers together and we divide by 3. And when we did that, we got the average time is 11.74 seconds. This is the average time for 5 cycles, but we want to know the period. Yes, the period is the time for 1 cycle. Then what we had to do in this case, this is the number of cycles. This is the time for 5 cycles. And if we want to calculate the period, then what we had to do is we had calculate the period equals to 11.74 seconds divided by 5. 5 cycles, 5 oscillations. Then this depends, the unit can be oscillations, can be revolutions, can be cycles. And we don't need to write that because we know that period corresponds the time for one cycle. And this is why we don't need to write really is 5 cycles. Then the period in this case equals to 2.348 seconds. And this is the time required for this particular pendulum to complete one cycle. Is 2.348 seconds. And we can see that the unit for the period, which is a special time, yes, is the time for one complete cycle, can be seconds, yes, can be seconds, can be minutes, can be hours, is any unit of time. And again, we don't need to write here seconds per cycle because we know the period is for one cycle. And this is why we don't need to write this is seconds per cycle. Another important variable we need to know is the frequency. The frequency is how many cycles can the system execute, in this case the pendulum execute in 1 unit time, per unit time. Yes. The unit time can be seconds, can be minutes, can be hours. Yes. And to calculate that, yes, we need to divide the number of cycles divided by the total time. Then in this case, because we already know the number of the time for 5 cycles, then we can calculate the frequency. And the frequency in this particular case will be 5. And I want to write here cycles because it's an option if you want to keep that unit or if you want to let me see, I cannot change here this to right. Try it again. Then we need to divide 5 cycles divided by 11.74 seconds. Then the answer is 0.4259 cycles per second. In this case is how many cycles can this pendulum execute in 1 second? Just half of the about half of the oscillation. Yes, in 1 second can move from here to here. Yes, this is the pendulum can move in one second. Then sometimes you can write in this way the answer, but also you can write this one like 0.429 1/second. This is another way you can write the same thing. And if it's frequency, then the people will understand it's 0.4259 cycles per second if you write like that. Also, another possibility can be, I will write here, 0.2. And 1/seconds has a special name, it's called hertz, and it's here. Yes. Then how what can be the possible units for frequency? Can be revolutions per second, for example, can be cycles per second, turns per second, revolution per minute. Also, we can write like that, revolution per minute, or can be hertz. Hertz means 1/second. This is another way we can write 1/second, a second to the -1 power. Now we know this is the period, this is the frequency, and this is the frequency. Then another relation we can find between the period and frequency is this. Is period and frequency, they had a inverse relation. And we can just test here quickly to find, if we know the period is 2.348, then we can calculate the frequency 1/period. Period is 2.348 seconds. And if you calculate, you will get the frequency is 0.4259 hertz. You will get the same value. Then once you know the period, you can calculate the frequency. But if you know the frequency, then you can calculate the period, because they had inverse relation. And we can see the inverse relation in this equation. We can see in this case the period equals to time over the number of cycles, but here the frequency is the number of cycles divided by the time. Then here we want to calculate the frequency of a vibrating system that has a period of 0.5. Yes, and if we know the period equals to 0.5, and we will write here period equal 0.5 seconds, and the frequency equals to 1/period. Remember, the period is the time for one complete oscillation. Then the period equals to 1.5 seconds. Then the frequency equals to 1/second. Or we can say also the frequency equal to 2 hertz. Yes. Then if the period is 0.5 seconds, means the time to complete one complete vibrations is 0.5 seconds. But if the frequency is 2 hertz, means this vibrating system can complete 2 cycles in 1 second. Yes. And how many cycles in the unit time? How many cycles? 2 cycles per second. Then another possible answer, yes, if we want, can be like that, 2 cycles per second. Yes, 2 cycles per second. Then any of this one are the right answer. And sometimes it's easier if we can interpret, we can understand any vibrational motion if we are able to represent this vibration in a displacement versus time graph. Then here we had a spring mass system, and if we just move the spring, yes, apply some force to the spring, then they start vibrating. Yes, they start moving back and forth. And if we can register this back and forth motion, let's say we can put some ink on this mass, and we can put some paper and move the paper while the mass is vibrating, then what we can see is something like that. Yes, what we can see is moving up, then down, down, maximum displacement, then it's moving back, and this is the maximum displacement in the opposite direction. And this motion will be continuous, will be continue with the time. Then we can see something like that. Here is the animation. We can represent that as is moving up, down, and at the same time we are graphing what happened with the motion. Then at the end we can see something like that. Yes, we had time in this axis. We had here the distance. In this particular case, the distance corresponds to the amplitude. Yes, with the maximum amplitude, and this line corresponds to this line. Yes, correspond to the equilibrium position. And in this case, we can see clearly this is the equilibrium position. If we had this graph, distance versus time, we can identify, using this graph, we can identify the amplitude of the motion as is the maximum displacement from the equilibrium position. And this is the amplitude, this is the amplitude. Also, we can identify the cycle as cycle is complete vibration. Coming from this point to this point is one complete cycle. Yes, this is in this position, and then return to the original position is one complete cycle. Yes. Also can be from this point to this point. Yes, is this position. Then we can measure the one complete cycle. But it's easier just from this point to see we had one complete cycle. Then why the distance versus time graph are important? Because you can identify, using this graph, you can identify, for example, the amplitude. You can identify also the complete cycles. In this axis we had time, we are able to identify the time from here. Remember, the time for one complete cycle is a period. Then we can identify the period, and we know if we know the period, we know the frequency, because the frequency is the inverse of the period. Yes, just remember, this is the period. This corresponds to the amplitude. This is the period, and the frequency is the inverse of the period. And all these variables we are able to identify if we had displacement versus time graph. Now we want to talking about some special vibration. That special vibrations are called waves. Waves are traveling vibrations in a medium. Then there are some waves need some mediums to travel. For example, in this case, the vibration is traveled through the water. Then the water is the medium. Yes, the medium. Then that vibration, that back and forth motion, can travel through the water. In this case, we had the sound. We cannot see the sound, but we can hear the sound. Yes. Then that our vibrations can travel, for example, in air. Yes, in air. Then that there are some kind of vibration need a medium to travel. And some of these vibrations are, for example, the sound. One of the examples is the sound. Now, depend how that waves traveling in a medium, we can see two different kinds of waves. One is longitudinal, the other one is the transverse wave. And I want you to watch this video, and then we want discuss what are the longitudinal waves and what are the transverse waves. And let's watch this video first.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
And let's move to the next slide. Then we say there are two different kinds of waves. One is longitudinal. In longitudinal waves, the vibration or the wave travel in the same direction of the particles of the medium. Yes, in this case, the particles of the medium vibrate in this direction, and also the wave travel in this direction. Yes. Then wave and the particles of the mediums move in the same direction, as parallel each other. But in case of transverse waves, the particles of the medium, they vibrate in perpendicular direction to the wave motion. And in this case, the particles of the medium vibrate in this direction, but the wave moves in this direction, yes? In this direction. Then it's 90 degrees. They are perpendicular. Some examples of the longitudinal waves are the sound waves, and some examples for the transverse waves are the electromagnetic waves, or waves on a string, like we saw in the previous video. Another thing I want you to see, you see, in case of the longitudinal waves, there are some parts where the spring, the parts of the spring, they are closed, but in the other regions of the spring, the parts of the spring are apart. Yes. Then I want you see this one, this part, and this part, because we need this one to understand how the vibration is compressed the spring and is moving through the spring. It's important to mention here the particle of the medium doesn't travel. Yes, they vibrate, but they doesn't travel. Just the vibration is traveled through the particles of the medium. Yes, and if we just put some particle here, yes, some mark here, this like the particle of the spring, this particle is not going to travel, just this is going to vibrate like that. Yes, vibrate in this direction, but what is traveled through the spring is the wave. Yes, it's not the particle of the spring, it's just the wave. And this is important because now we want to discuss the special kind of wave is the sound waves. Sound waves, as we mentioned before, is longitudinal, means the particles of the medium and the way they travel in the same, is the particles of the medium vibrate in the same direction the wave is traveling. And in this case, we are going to the medium in this case is the air. Yes, is the air, is the medium, how the sounds of the wave can propagate, can travel. Then the sound waves are traveling this direction, and also the particles of the air are also vibrate in the same direction. Then what we can see, remember we saw here some regions where the spring is closer and the spring here, the parts of the spring are apart. The same thing happened here. Then when the sound wave is traveling through the air, we can see there is some regions where the molecules of the air that vibrate closer, but in another part, in another portion, in another zone of the in another zone, we can see the particles of the air, they vibrate. They are apart, yes, they like here and here. Then we can identify these two regions. Then in these regions is called the condensation region, and is also called the compression. But the other region where the molecules of the air are apart, then is called the expansion region, also called rarefaction zone. Then this is how is creating these two different zones. The compression and expansion is the air is compressed and expand, compress and expand, compress and expand. Is how the sounds can travel through the air, creating these different zones, different compression and expansion zones in the air. Remember, these regions, compression is called the condensation, and the expansion is rarefaction region. Another thing is what I want to mention here is the humans can hear only some particular frequencies. Remember, we mentioned the frequency. We can hear some particular frequencies. Then what frequencies we can hear between the 20 hertz and 20,000 hertz or 20 kilohertz. And this is the range of the frequency we can hear. In this slide, we can correlate the graph of the condensation and expansion region when the sound is traveling to the air with the displacement versus time graph. And in this case, we can see the condensation regions correspond to the maximum amplitude from the equilibrium position, but the expansion regions correspond to the maximum amplitude, but in opposite direction from the equilibrium position to the maximum amplitude, but in opposite direction to the equilibrium position. Yes. And here we can see this is the compression or the condensation zones or regions. Here is the expansion correspond to this part of the graph, and this again is condensation correspond to this part of the graph. In this case, because the molecules of the air are closer, correspond to the high pressure region, and this part, the molecules are apart, then is correspond to the low pressure region. Then in this slide, I want to review what variables we already studied and the variables we need to know to describe any vibrational motion, but also I want to mention few more variables we need to know. Then let's start with this is the graph of the displacement versus time. Yes, we had displacement in y-axis, time on x-axis. Then we want to review some variables. The first is the amplitude. The amplitude is the maximum displacement from the equilibrium position. Yes, this is the amplitude. This is the amplitude in opposite direction from the equilibrium position. Two new terms. Then the maximum amplitude from the equilibrium position is called crest, as wave crest is this one. If the maximum amplitude is in the opposite direction, then this part we call the wave throat. Yes, throat is this part. And also we know the period. Period is the time for one complete vibration, is the time that takes the wave or the vibration to travel from this point to this point, yes, for one complete cycle. Yes, this is the time for one complete cycle. And frequency is, we know, is the inverse of the period, but we know is how many cycles can the system or can the vibrational system execute per unit time. It's how many cycles per second, for example, and how many cycles per minute. And this is a new term, and it's very important because it's a special distance. It's the wavelength. Wavelength is the distance from the distance wave travels during one period. Yes, is the distance the wave travels during one period. Is this distance. And in a displacement versus time graph, we can identify the wavelength from the distance from one crest to the next one. Yes, this is one cycle. Or can be also the distance from one throw to the next one. Yes, can be this one also, can be one cycle. Can be also is where we come back to the original position. If we start here, one complete cycle will be here. Yes, stop, because here is we start again in the same point. Then here is also. Then there are different ways we can identify the wavelength in the same graph. Yes, the same graph. But important thing is you have to remember is the distance the wave travels during one period, as this is the wavelength. In this slide, what we can see is we had two different waves, but the waves they had the same frequency, they had the same period, yes, it's the same period, the same frequency, the same wavelength, but they had different amplitude. Yes, they had different amplitude. Yes, the wavelength, the time to travel one complete cycle is the same. Yes, it's the same. The period is the same. Yes, we can see here the period is the same. Yes, from here, the time is the same. But just the amplitude are different. The maximum distance from the equilibrium position is different. And the amplitude is different. In the next examples, what we had is we had two waves that they had the same amplitude. The distance from the equilibrium position is the same, but they had different frequency. Yes. The red one traveled more cycles in 5 seconds, traveled more cycles than the blue one. Yes. This is why the frequency is different. How many cycles per unit time is different. If the cycle if the frequency is different, then the period is different. Remember, the frequency equals to the inverse of the period, or the period equals to the inverse of the frequency. And if the period and the frequency from these two waves are different, the wavelength is different. As here is the wavelength is the distance the wave travels from this point, there is this distance, but in this case will be just this much. And in this case, the wavelength for the blue one is larger than the wavelength for the red one. The period for the blue one is greater than the period for the blue one, and the frequency for the blue one is less than the frequency to the red one. Now we want to get the relation that correlate the wavelength, which is a distance, the period, and the speed of the wave. One important thing, and I want you to remember this one, this concept is the waves travel, any wave travel at constant speed in one particular medium. For example, the sound in air at the same temperature travel at the same speed, 343 meters per second. As at room temperature in air, the speed of the sound is 343 meters per second. Then is the waves travel at constant speed in a particular medium. Sometimes we can say also in a particular conditions, in some particular conditions. Then, but this is important. The waves travel at constant speed in a particular medium. Because the waves travel at constant speed, then and it is a motion, then we can use the equation that describes the motion at constant speed. Is velocity equals distance over time. Yes, this is the equation we described in the previous chapter. Yes, this is the equation that describes the motion at constant speed. Velocity equals distance over time. In this particular case, we will focus in the special distance. In this distance, the wave travel in one period. What is that distance? Is the wavelength. Yes, and we say we can measure the wavelength from here to here, or from here to here. Is the same distance. Then that is the special distance, is the one wavelength. But this wave travel this distance in a special time. One time, what time is the period? Yes. Then this time is one period. That is, this wavelength travel in one period. Then this is the equation we can apply to describe the motion of any wave. Yes, any wave. And I want here to show, here we had this. I forgot here to mention the Greek letter we use to identify the wavelength is lambda, and is this. This is the letter is to identify the lambda, the wavelength. To identify the wavelength is a lambda. Then here we had is the period. Now we know the frequency equals to 1 over period. Then let's write this one like, we can write this one like 1. Yes, it's the same thing. Yes, it's the same thing. Lambda times 1 is lambda, then over period. But this is a frequency. Then this corresponds to frequency. And this is the equation we had. This is the equation we had right here. Then we can apply either this equation or this equation. They are the same equation. They are similar equations to describe any wavelength. Yes, where this v corresponds to the speed of the wave, lambda corresponds to the wavelength. Yes, and capital T corresponds to the period. Or we can also apply this equation. V is the velocity equals to the wavelength times the frequency. Yes, we can apply either this equation or the other one. And in this problem, we had a sound wave which has a frequency. Let's write here frequency. Frequency equals to 60 hertz. Yes, this is the units for frequency, hertz, and the wavelength with the lambda 1 point. And remember, the wavelength is a distance. This is why the units is meter. And this is why the units is the units of the distance is a meter. Then we want to calculate what is the speed. Then we know the wavelength, we know the frequency, then we can calculate the speed of the sound, as the speed of the sound. And let's calculate the speed of the sound. Then it's wavelength is 1.27 meters times 260 hertz. But remember, 1.27 meters times, and I want to write this 1 over second. And because it's a speed, the units we expected is meter per second. Yes, and we see meters times 1 is meter over second, which are the units for speed. And if we multiply these two numbers together, we will get 330 meters per second. Then if the sound has this frequency, and this is the wavelength, this is 1.27, is long wavelength, yes, because it's low frequency, then the velocity is 330 meters per second. Then let's now go with the next problem. In this case, we had a sound wave that has higher frequency. Yes, the other one was 260 hertz. Here we had 2,500, almost 10 times more the larger frequency. And in this case, the frequency equals to 500 hertz. And in this case, we know the velocity or the speed, the move, and we know this is the speed because it's meters per second. It's 330 meters per second. Then we want to know what is the wavelength. We don't know. Then we know the frequency, we know the speed, then we need to solve for the wavelength. And let's write here the equation. And we divide, because we need to solve for the wavelength, we divide by the frequency. Then finally we have the wavelength equal frequency. It's 330 meters per second. And I want to write in this way. Frequency is 2,500. And remember, hertz is 1 over second. 1 over second. Because wavelength is a distance, we expected units. We expected meter units. As this is, we expected unit meter as units. And let's check the units. I will just do in this part. I will check the units. What we had on top is meter per second. And we had in the denominator is 1 over second. And we say if we had division, yes, we can apply the same rule we apply for numbers. We convert the division into the multiplication and we flip the fraction. Yes. Then we had 1 over second will be times second over 1. Seconds cancel out, meters over 1 is just meter. And this is the units we expect. Yes. Then lambda, the lambda must be in meters, the wavelength. And if we divide these two numbers, we will get 0.13 meters. Because the answer is in centimeters, what we can do is just we multiply by 100. Yes, then lambda is the same, 13 centimeters. Then what we will do in the next slide, I want to compare these two results in the next slide. we had 260, we had 1.23, and the velocity of the sound is 330. In this case, we had the same velocity of the sounds, but we had different frequency and different wavelength. And let's here write these values, what we had for one case and what are the values we had for the other case. And in the first problem, we had the velocity, the speed is 330 meters per second. We had a frequency of 260 hertz, and we had the wavelength is 1.27 meters. In the second case, we had the same speed, but the frequency in this case is 2,500 hertz. And the wavelength is, let's keep in meters because we want to compare the values. Then what we can observe here is, in this case, if the frequency increase, is what happened with the wavelength. Let me write here. If the frequency increases, yes, this is happened 260 hertz to 2,500. The frequency increases. What happened with the wavelength? Here is 1.27 meters, but here is 0.13 meters. Okay. Then the relation between frequency and wavelength is inverse relation. And we can see this one if we just analyze the equation. As we have this, if we divide by the frequency, then we have this. I will write here this. If the velocity is constant, in this case, then if the velocity is constant, yes, if the velocity is constant, we can see if we just remember the line test, lambda is on top, frequency is on bottom, then they are inverse related. Yes. Then if the frequency increases, the wavelength is going to decrease. Let's try to graph this one. See if I can do it here. Let's try to graph this one. This corresponds to, this is the representation of one complete cycle for the first wave. Yes, for the first wave, for this one. Then it's 1.27 from this point to this point. We had 1.27 meters. Yes, this is, we had 1.27 meters. Then what happened if we write the equilibrium position? Now, how we can compare this one with the second one? What happened with this? The wavelength frequency increases. Yes, frequency increases, then the wavelength is decreases. Then we will have something like that. It's decreasing by 10. Yes, it's decreasing by 10. Here is about 1.3. It's decreasing by is the wavelength is decreasing about 10 times. Yes, 10 times. Then I will do 1, 2, 1, 2. Then we will have something like that. Yes. Then this is how we can see. Here I am going to correlate the amplitude. Just I want to correlate is the frequency and the wavelength. Yes. If the wavelength is larger, then the frequency is small. Yes, how many cycles per unit time. But if the wavelength is a small value, then what happens is the frequency is increases. There's more cycles per unit time. Yes, per unit time. Then this wave is low frequency. This wave corresponds to high frequency wave. Yes, high frequency wave. Then we know when the sound is represents some sound, this is a fork. Yes, we strike a fork, this produces some sound. This sound travel through the air, and this produce when this travel condensation and extension sounds. And in this way, these vibrations can move through the air. And then what happens is these vibrations can reach to the eardrum, and the eardrum sends nerve signals to the brain. Yes, and the brain can interpret this signal as a sound. This is the general idea how we can hear the sound. Yes, this is a general picture of how we can hear any sound. And in this picture, what I want just to mention is what frequency we can hear. Is we can hear the frequency from 20 hertz to 20,000 hertz, means from 20 hertz to 20 kilohertz. Below to this value and above to this value of frequency, we cannot detect, we cannot hear that sound. We cannot hear that sound. Then below to 20 hertz, we call this region as infrasound. And for example, the elephants can hear that vibrations, that sound with this frequency. And above this value, 20 kilohertz, also we cannot hear that sound. Yes, this corresponds to the ultrasound region. And for example, the bats can hear that frequencies, the sounds at that frequencies. In the next presentation, we will discuss what is the sound intensity and what it is important. But now remember, the humans can hear some particular region of frequency. We can hear from 20 hertz to 20 kilohertz. This is the frequency we can hear. Also, in this slide, we want to talking about the sound speed in different materials. Remember, the sounds requires a medium to travel. As the sounds requires a medium to travel, but depend of that medium that determines the velocity of the sound. Yes. For example, we had three different mediums. We had gas in this part. It's carbon, helium, hydrogen. This corresponds to gas. Then we had water and seawater. This corresponds to liquid. And the last part we had solids. There's lead, glass, and steel. This corresponds to. Then what we can see is the sounds. We can see here we had the velocity of the sound, and we can see the velocity of the sound is larger in case of the solids than the liquids or gas medium. Yes. When the sound propagates in solids, the velocity is larger. And the reason is because in case of the solids, the molecules are closer, then the wave can propagate efficiently. As this is why the speed of the sound is greater in case of when the sound propagates in solids. With this table, I want you had idea, or you had some reference points to think when we were talking about different velocities. How high is one particular velocity? For example, if we had 1 meters per second is the speed we can walk, yes, and this is equal to 2 miles per hour. The speed in the school zone is 22 miles per hour. This corresponds to 10 miles per second. Then is the velocity or the speed, yes, in the school zone is 10 times greater than when we are walking. Yes, this is how we can compare these two. Now, the maximum speed in the highway is about 67 miles per hour. Then this corresponds to 30 meters per second. Then is the speed in the highway is 3 times larger than the speed in the school zone. Yes, then we can think in that velocities. Now the speed of the sound is the speed of the sound in air. This is just, I just round the number because it's easier to remember. Then the speed of the sound is about 300 meters per second, means it's 670 miles per hour. Is how many times larger than the speed in the highway? Is 10 times larger. The sounds travel 10 times faster than the speed in the highway. Yes, it's 10 times larger, faster. Yes, the sound travel 10 times faster than the speed in the highway. Now the last thing, and we will discuss this, the speed of the light in the next chapter, but just I want to mention the speed of the light. The speed of the light is, you see we have here 8 zeros, means we can write this one like 310 to the power 6, 1, 2, 3, 4, 5, 6. Then how many times is greater the speed of the light compared with the speed of the sound? Is 1 million times. Yes, it's 1 million. Then the light travels 1 million times faster than the sound. It's 1 million times faster than the sound. Again, I just doing this one, just you had idea of when we are talking about the 300 or 350 and 300 millions, yes, how we can compare that velocities. And this is why if there is a lightning, yes, we can see first the flash of the lightning, and then we can hear the thunder few seconds later. This is why, because the speed of the light is 1 million times greater than the speed of the sound. Yes, this is why. Now we want to concentrate in just the velocity of the sound in air. Yes, this is, remember, the velocity of the sound is different depending on what material the sound is traveling. Yes, but now we will concentrate just in one medium. In what medium is in the air. Then we will concentrate what is the velocity of the sounds in air. Then there is one thing, is the air temperature influence the speed of the sound, as how fast the sound can move depend of the temperature of the air. Then here we had few examples. Here, for example, for case of minus 1 degree Celsius, the speed, here is the speed is in meters per second, is 330.4 meters per second. But in 21 degrees Celsius, the speed is 343.6 meters per second. But if the temperature is 45, yes, it's hot, is 358 meters per second. Then what happens is, as the temperature increases, the molecules of the air move faster. Means the molecules of the air increase its kinetic energy. Because the sound waves increase its speed, then the sound wave increase its speed due to the increase of the kinetic energy of the air, of the molecules of the air. Then one important thing is here is what was found is the velocity of the sound increase in 0.60 meters or 0.6 meters per second each degree Celsius. Yes. Each degree Celsius, the speed of the sound increases in 0.6 meters per second. Another thing is the speed of the sound at 0 degrees Celsius is 331 meters per second. And we will see why these two information, why to know these two is important. Let's write here this information we had from the previous slide. And we say each degree Celsius, the speed of the sound increases in 0.60 meters per second. Also, we know if the temperature is 0 degrees Celsius, the velocity of the sound in air is 331.0 meters per second. And now let's try to graph this velocity of the sound in meters per second, and let's write here the temperature in degrees Celsius. Then what we know one point on this graph, yes, we know if the temperature is 0 degrees Celsius, the velocity is 331 meters per second. Then this value is, we can think is right here, yes. This corresponds to the y-intercept, is where the line crosses the y-axis. In this case, the y is the velocity of the sound. Then this value corresponds to 331, is this value. Now what happened is, we know the velocity is increasing in 0.6 each degree Celsius. And we can associate this, we know this one, as, remember the slope of the line? In this particular case, the slope of the line is delta y over delta x, but in this particular case will be delta is the change in velocity, change in time. But we know in 1 degree Celsius, yes, in 1 degree Celsius, the velocity increases by 0.60 meters per second. Then 0.60 divided by 1 is 0.60 meters. Then we know the slope of this line is 0.6 meters per second. Yes. Then remember is rise and run. Yes, is rise and run. Yes, rise and run. And we rise. We will see something like that. Yes, we move one and we up, we rise 0.6. It's complicated here too. Then finally we had this point, this point, this point, and we can get more points, yes, but we had something like that. Then the slope of the line let me write here the slope of this line, 0.60 meters. Yes, this is run. Sorry, this is rise. This is run. Yes, this is right. This is run. And this is how we can get more points on the line. Just more points on the line. And we know the relation between the velocity and the time is a linear relation. Yes, it's a linear relation where the y-intercept is 331 and the slope of this line is 0.60 meters per second per degrees Celsius. Because it's a line, we can just write the equation of the line, the general equation of the line. Now, let's write this one using our variables. Y. Y is the velocity of the sound. A slope. We know the slope is 0.60 meters. Y-intercept. Y-intercept is the velocity of the sound at 0 degrees Celsius. As is 300. Oh, here I missed the variable. Yes, let me go back. Yeah. Then this is the slope. X in this case is the temperature. Yes, this is important. Is the variable plus the y-intercept is 31 degrees Celsius. And I'm going to rewrite this one in the way it's in your textbook. It's 331. It's the same thing, but just I want to write in the same way is in your textbook. Yes, these two equations are the same, but in your textbook is like that. Then using this equation, you can calculate the velocity of the sound at any temperature. Yes. Then if the temperature is 20 degrees Celsius, you just multiply 0.6 by 20 at 331, and you will get the temperature of the velocity of the sound at this particular temperature. One important thing is that if we use this equation, the temperature must be in degrees Celsius. Yes, the temperature must be in degrees Celsius. And these equations allow to calculate the velocity of the sound at any temperature, but the temperature must be in degrees Celsius. And now we had here the equation. Yes, the equation is in your book. Then just don't confuse this correspond to the velocity at present temperature. What is the present temperature? Is the temperature you want to calculate the velocity of the sound. Yes. This is the slope, and this is the y-intercept. In this case, is 331. As if we use meters per second, if the equation, the unit we use is meter per second, V sub 0 is 331. And in your equation sheet, I replace the V sub 0 by 331. And you don't have to memorize that value. And for example, if we want to calculate what is the velocity at 30 degrees Celsius, then we just replace T by 30 degrees Celsius. We multiply these two values, which correspond to 18, must be 18.0 meters per second, 18 meters per second plus 331. Then the speed of the velocity or the speed of the sound at 30 degrees Celsius is 349 meters per second. Also, we can do exactly the same procedure, but just if we want to calculate the velocity of the sound in feet per second, then what we had to use this equation, because in this case, the temperature of the sound increased by 2 feet per second each degree Celsius. Then this is why in this case the slope of the line is 2 feet per second per degree Celsius. And this is 2 feet per second per degree Celsius. And in this case, the the velocity of the sound at 0 degrees Celsius in feet per second is 1087 feet per second. As this corresponds to this value. And this equation, using this equation, we can calculate the velocity of the sound at any temperature, but in feet per second. Yes, in feet per second. And let's now apply this equation. Then we want to calculate what is the speed of the sound at room temperature. If the temperature equals to 20 Celsius, we want to know what is the velocity of the sound. And what we need to do is we need to write here the equation as the velocity equals, but we know this value. Again, in your equation sheet, you will have this value. I already include this value in the equation. Okay, then you don't have to worry for this part. Plus as 0.6 meters per second. I want to write this one. It's the same thing. I think it's easier. Let me write this one again. Meters. It's the same thing, okay? And then multiply by the temperature, but the temperature is 20 degrees Celsius. And this cancel out with this one. Then we multiply 0.6 times 20, which is 12. Then first multiplication, yes, and then addition. Yes, this is the order of operations. First we multiply 12.0 meters per second. You see, the only way we can add these two terms if we had the same units. You see, this is why this cancel out and we have meters per second. If we add these two numbers together, we will have 343 meters per second. Then the velocity of the sound, if T is the temperature is 20 degrees Celsius, the velocity of the sound is 343 meters per second. And now let's try to do this example, but here the temperature of the air is 46 Fahrenheit. And we have to be careful, it's Fahrenheit. Remember, this equation works if the temperature is in degrees Celsius. And we have to be careful in this case because we had to change the temperature from Fahrenheit to Celsius. Yes? And here the problem said they want we give the answer in feet per second. If the problem doesn't say what units they want, in what units they want the velocity, then you can choose either meters per second equation or feet per second equation. But in this particular case, we need to calculate using this equation because we want the velocity of the sound in feet per second. Then we know the temperature is 86.0 Fahrenheit. Yes. Then we need to calculate this in degrees Celsius. Then we need to use the equation that correlate, that allow us to convert Fahrenheit into degrees Celsius. And let's just equals to 86 minus 32. Then here we have 5 divided by 9 equals to 54. And this is 0.0, it's 54. Then here you had two options. You can multiply 5 times 54 and divide by 9. Also you can simplify this. You see, 54 divided by 9 is 6. 5 times 6 is 30. This is 30 degrees Celsius. And also, let me write here the other way. Yes, and this is the answer. The other way, it will be like, let me write here. And we can multiply 5 times 54, and this is 270. Divide by 9, and this one will be 30. The same answer. Yes, the same answer. Then either way is right. Then now we know the temperature is 30 degrees Celsius. Then now, after we know the temperature in degrees Celsius, and here should be 30.0. Yes, if we want to give the right number of significant digits. Let me write here correctly. Yes, 30.0. Now let's calculate the velocity. Then the velocity of the sound equals to, we know this is the velocity of the sound at 0 degrees Celsius in feet per second is 1087 feet per second plus 2 feet per second times the temperature. Then we cancel out the temperature, and now we just multiply first, yes, and then we add feet per second plus 2 times 30 is 60 feet per second. Again, we had here feet per second. We must have here feet per second. It's the only way we can add these two numbers together. And if we add these two numbers together, we had 1147 feet per second. This is the answer. Then if the temperature is not in degrees Celsius, we need to do 2 steps in order to complete the problem. The next thing, I want just to give an idea about the simple pendulum, the amplitude and mass variation lab, but I will upload the complete description of the procedure and the lab sheet you had to complete. And I want just to give an idea. You had to download the procedure and you had to follow that procedure. I just write in detail, step by step. Again, I want just to give an idea what you are going to do. And this experiment has 2 parts, mass variation and amplitude or angle variation. Then what we are going to do in the first part is we want to find what is the effect of the mass of the pendulum if we keep constant the length of the pendulum, yes, this is the length of the pendulum, and the amplitude, the angle, the distance from the equilibrium position. The way we will control the distance from the equilibrium position is using the angle. Then in the first part, we will keep constant the amplitude and the length, but we will change the mass. Then we want to know what is the effect of the mass and the frequency of the pendulum, where the pendulum is oscillating. Yes, this is, we want to calculate if there is, what is the effect of the mass on the frequency. Yes, how many cycles per unit time. Yes, this is, we want to determine the effect of the mass on the frequency. In the second part, we want to keep constant the length and the mass, and we want to know what is the effect of the amplitude on the frequency of the pendulum, of the oscillation of the pendulum. Again, in the second part, we will keep constant the length, yes, and the mass. We are not going to change the mass, but we will change the amplitude, and we will see what is the effect of the amplitude on the frequency of the motion of the pendulum. And how we will do that then? in the procedure, you will find a link. You will click on this link, and then you will find some program that allow you to do that. Then just I want to mention, when you click that link, you will find some in the screen will appear something like that. Then just I want you to get general idea. In this part you can control, you can change the length of the pendulum. In our case, for this experiment, for both parts, the length of the pendulum will be always 1 meter, as we want to press here, move this one to the right to 1 meter. Mass will be changed in the first part, in the second part will be constant, as will be constant. How we will change the mass? Just move this button, just move this button from left to right, press here and move, and you can change the mass. The gravity, we will just keep constant. The gravity will be the Earth gravity, then you have to select the Earth as in the gravity. Friction, none, as we will consider there is no friction in our experiment. Another thing you need to activate is the stopwatch. Once you activate the stopwatch, this will be appear here is the stopwatch. This button is to reset, and this button is to start the stopwatch. And here is the pendulum. Yes, here is the pendulum. How we will change the angle of the angle of the pendulum? Just you click on the mass and drag the mass to the pendulums you desire. For example, here is an example, is just you click on the mass, just drag the mass to 15 degrees. This angle will change, and in this way you can change the angle. In the first part the angle is constant, but in the second part we will change the angle. Then once you have the parameters you need, then just you drag the pendulum to the angle you need. Just release the pendulum. Once you are ready, yes, you need to count 5 complete oscillations. 5 complete oscillations. Then once you are ready, this starts swinging, yes, like that. Then once you are ready to start count 5 complete oscillations, just because the pendulum is going to swing it all the time you allow to swing. Then just you press start when you are ready to count 5 complete oscillations. When you complete the 5 oscillations, you press here again, stop, and this is the time for 5 oscillations. Okay, this is the time for 5 oscillations. To reset the angle, just click in the red button here, and you will get again the pendulum at 0 angle in this position. Okay, again, this is just I want to give an idea. You had to read the lab sheet, the procedure, and the lab sheet. You had to complete the data. If you had any question, you can email me, but I just want to give a general idea what you are going to do in the experiment. Nice. Then I think this is all for today. Then please stay safe, and if you have any question, just you can email me. Just you can join to the conference I am doing one time in a week. Okay, bye bye.